Hello everyone, so today I'll be solving the LeetCode daily challenge for June 15th. So this is a medium problem and it's a binary tree problem. So the statement of the problem says that, well, you can read the statement of the problem, but in essence what it says is that the tree has multiple levels. The root is at level 1, the root's children are on level 2, and the grandchildren on level 3, so forth and so on. So you could have a fourth, a fifth, and other levels. So the problem wants to know at which one of these levels has the biggest sum of the values inside the nodes. So for example, the green box is the first level, which only has the root. So the sum at level 1 is 1, only the root. The yellow box is the second level, level 2, and it has two nodes, 7 and 0. So the sum of all the nodes on this level is 7. And the third level is the red one. It also only has two nodes, 7 and minus 8, so the sum of level 3 is minus 1. Note that level 3 could have two more nodes, because the node 0 could have a left and a right child, but it doesn't have. So the more in depth you go, the bigger could be the number of nodes you have to account for. So this makes the problem a little bit harder, right? So in this case, the answer would be 2, because the yellow level has the biggest sum, which is 7. It's bigger than 1 and bigger than minus 1. In order to do that, one solution that fits very well with the problem is breadth first search, or BFS. And the reason why I think the solution is best for this problem is because BFS actually tracks the levels exactly in the way that the problem states. So for example, BFS starts at the root and it operates at the root level during a certain amount of time. And only after the BFS finishes one level, it goes to the next level. So it always tries to go further away from the root, but it only goes further after it finishes all the nodes at the same distance, right? So for example, it goes to the root and it finishes the only node on the root and goes to the next level. And only after it finishes all nodes that are one distance away from the root, it goes to the nodes that are two distances away from the root, right? So BFS, because of that, is a really good solution to solve this problem. And in order to solve a problem using BFS, we have to use a data structure called queue, right? So I'm not going to explain exactly how the queue works here, but I'm going to show you how to visualize the BFS using a queue. So using a BFS, first we have to add to the queue all the nodes of a certain level. So first we add all the nodes of the first level, which is only the root. So we add it, and we're gonna iterate through all the nodes of this level and add their children. So at level 1 we only have the root, and then we add the children, 7 and 0. After that, we have the nodes from two different levels, right? We have from level 1 and level 2. But we want the sum only of the level 1. So we get the sum from level 1, and the sum of level 1 is just 1 because it's just the root. So all we have left are nodes from level 2, the yellow nodes. So we have to repeat this process again. First, we add all the children from all of these nodes, which are 7 and minus 8. Then we have only the nodes of two levels, level 2 and level 3, the yellow and the red nodes. So we can now compute the sum of the nodes on level 2, the yellow nodes, which is 7. And all that's left is nodes from level 3. So we could repeat this process once again. We first add all the nodes from level 4. In this case, there are no nodes on level 4. And now we compute the sums of nodes on level 3, which is -1. So at all times, we have nodes from 2 different levels. At the beginning, I'm gonna start all over again. At the beginning, we had level 1, we had nodes from level 2, and compute the sum of level 1. Now we add the next level, and compute the sum from level 2. Then we add the next level, which is none, and compute the sum from level 3. So a QDR structure here is really important for us to solve because it makes it easy for us to keep track of the level of the nodes. There may be other different ways to solve this problem, but the queue makes it very convenient. So the pseudocode for that is more or less like this. We're going to initialize an empty queue. We're going to add the root node to the queue. And we're going to iterate through this queue until it's empty. Because after it's empty, it means that we went through all the levels and there's nothing else to add to the queue. So we're going to reset the sum at the current level. So we're going to start counting from 0 at the current level and iterate over all the nodes from the current level, right? So we're going to pop this node from the queue. We're going to remove the nodes from the current level from the queue. We're going to add its value to the sum of the current level. And we're going to add the children of this node to the queue. These children are the next level nodes, but we're not going to iterate through these children. We're just going to iterate through the nodes on the current level. So this step 2, iterate over current level, is very important that it doesn't go over the nodes of the current level. And at the end, we push the node children to the queue, and we check to see if the current level is the one that has the maximum sum or not, and we update the answer accordingly. So I'm gonna try to implement this now in the code. There might be some mistakes, but let's do our best. So first we can initialize our queue. I'm gonna call it BFS queue, and this is an empty queue for now. So the first thing I'm gonna do is I'm gonna add the root node to this queue. And now this queue has the first level, right? All the nodes from first level. So I can start my iteration. I can start summing the nodes of the first level and adding the nodes of the second level. So while the BFS queue is not empty, so we need to iterate until we don't have any levels more to add to the queue. So while it's not empty, we're gonna start doing the iteration. So here we have to iterate through all the nodes of the current level, right? So how many nodes we have in the current level? Well, in the current level, we only have the root node. Level 1 only has one node. So we can define an integer being the BFS queue.size, right? So this is 1 for now. And we're gonna iterate through all the current elements in the queue. And here, inside this for loop, we only have the current elements from the current level. So we're gonna add the value. So first we're gonna get this element. So we have to do tree node current is gonna be BFS queue.front. So here we just got the first element in the queue, and there we're gonna remove it from the queue, BFS queue.pop. So here current is the first element in the queue. I'm gonna add the value of current to the sum of the sum at the current level. So sum at current level curvel. So I'm adding to the sum at the current level. So I didn't define the sum at current level, so this is a variable that I'm gonna count for each level that I'm iterating through. So first I'm gonna define it here outside here, sum at current level, and I need to reset this for every level that I'm counting the new nodes. So for level 0, it starts at 0 and goes to 1. Then at level 2, we have 7 and 0. We're gonna sum these nodes to the sum, right? So sum at current level equals 0. So I need to reset this every time I go to a new level, and that happens after I iterate through all the nodes on the current level. So I'm gonna sum the value of the node that I just popped from the queue, which is one of the nodes at the current level, to the sum. And in the end of the iteration, I'm gonna check if sum at current level is bigger than a max sum of all levels, I'm gonna update max sum to be sum at current level. And I also need to update the answer. So if the sum at the level that I'm currently iterating through is bigger than the biggest sum I have ever found, it means that the current level is the one that has the biggest sum, right? So I didn't define these 3 variables, but I'm gonna define them now. So I'm gonna initialize max sum to be the minimum value that the integers can have. And this is important. I cannot assign it to 0 because we can have nodes with negative values. So maybe all the sums are negative, and if that happens, I cannot initialize max sum to 0 because max sum is gonna be bigger than all the levels, than all of the sums of any level, and that's not the correct answer. So I have to initialize it as the minimum value possible for integers. So I have initialized max sum, then I can initialize the answer. So the answer, we can say it's 0 or something. Actually, I don't even know if I need to, I don't need to give it a value. And then there's another integer, which is level. And we're gonna start level at 1 because the level of the root is the first level. So after we finish iterating through the first level and we check to see if the sum is the biggest sum we found so far, we can increment level. And it means that when we start over, we're at level 2, and we're gonna iterate over the nodes at level 2. The only thing that's missing here is that we need to push the nodes from level 2 into the queue for each node that is on level 1. In this case, we only have 1 node, and we're gonna push these 2 children. So what I'm gonna do is, let me see. Okay, so I'm gonna get my BFS queue and push the left node and the right node from each node that is in the level that I'm iterating. So in this case, one thing that I have to be careful about is that maybe if I push the left node is actually 0. So for example, this node, I don't want to push like a null pointer into the queue. So I have to check if there is a left node, and if there is a left node, I can push the left. Same thing as for the right node. So if there is a right node, I can push it into the queue. And by doing these steps, we guarantee that we're iterating through the current level, we're adding the next level, and this iteration will stop after we finish the current level. That's why at the beginning we have to get the current size of the queue and iterate only until we finish the current elements. Because as we iterate through the queue, we're actually adding more elements to the queue. So we need to stop only when we finish the current level. And this value, we know upfront what's the number of nodes at the current level. So I believe this should be runnable. I'm just gonna check to see if it's okay. We have to return the answer. And I believe this should run. Let's take a look. Okay, so there's something I missed here, which is the queue is not a queue of integers, it's a queue of 3 nodes. So that was a typo. We're actually adding the root node and the other nodes. So it passed. That's nice. We're gonna submit it and see if it works with all the other test cases, and it did. So to summarize, we need to use this queue, and we add the root to the queue because the root is the current level that we're iterating through. And we're gonna iterate until the queue is empty, because that means that we don't have anything to add to the queue. We have reached the end of the tree. We're gonna get all the elements that are currently in the queue, and we're gonna iterate through them. And inside here, I can calculate what's the sum of the level that I'm looking at. While I'm calculating the sum of the level that I'm looking at, I'm actually adding to the queue the next level, only the next level. But I'm not gonna add to the current level, because I'm gonna stop only after, I'm gonna stop when the nodes that are on the current level finish. So I need to remove them from the queue, and after I remove n nodes, I am only left with the next level, and I keep iterating. So this was my solution for the LeetCode daily problem for June 15th. It's a very interesting problem because it allows us to practice breadth first search in a very, almost like in its purest form, which is basically we are always getting the root, and then we're only going one step further from the root and calculating something onto all the nodes one step away from the root. Then if we don't find our answer yet, we can go one step further and calculate this new horizon. So we are always incrementing the horizon of nodes that we're looking at. So it's a really good problem to understand BFS, and I hope my solution helped you figure it out. Thank you very much.